Oops. All right, good morning, everyone. So this is just the problem we were working on Friday at the very end. So we just have to finish this guy up and then we can start talking about other things, right? So just to remind you, again, we have two particles, both of the same charge of Q, which are fixed along the y-axis, one at a distance d above the origin, the other one at minus d below the origin. And then here we're looking for an expression for the electric field anywhere along the x-axis. And then we want to plot that electric field versus x for those different locations, anywhere from 0 out to 4 times the distance d. And then determine the value of x that gives us the minimum value of the electric field and then the maximum value of the electric field. So what values of x give us the minimum and maximum value? So just to remind you, this is what we came up with the force. So we said the force then was equal to k times q squared times x divided by x squared plus d squared to the 3 halves. So good. So the next thing is we want to plot this thing. Now there's different ways to plot. One way is we could just grab our graphing calculator or some Mathematica or MATLAB or something and tell us to plot this thing. But we don't want to do that. We want to find better ways to actually plot. So one thing we can do to plot is we can kind of look at what's happening when x is small and when x is large. So what I mean is we can first look at what happens when x is much, much less than d. Right? So let's look at what happens when x is small. Well, if x is much, much less than d, what happens here? So x squared then becomes even much smaller than d squared, which means that denominator simply becomes what? Becomes d squared raised to the 3 halves, which is d cubed, right? So when x is much, much less than d, this thing is simply just d squared, which is d cubed, which means this whole entire function simply goes as x. Right? So when x is much, much less than d, that means that our force is simply proportional to x itself. So this function rises linearly for small values of x, which means when x is small, this thing is simply doing that. That's it. With some slope. Now the other extreme we can look at is what happens when x is much, much bigger than d. Well, what happens when x is much, much bigger than d? Well, if x is much, much bigger than d, then that means x squared is even much, much, much more bigger than d squared, which means the denominator simply becomes what? X squared raised to 3 halves, which is the same thing as x cubed. So for large values of x, this thing is proportional then to simply what? X divided by x cubed. But x divided by x cubed is simply equal to 1 over x squared, which means for large values of x, this thing then it has to look as 1 over x squared, right? It has to do something like this. Which means our function then has to be simply this thing connected. So this thing's going to rise up, turn around, do that. This is our function. Great. This is our force as a function of position. So again, small values of x, this thing has to increase linearly. Large values of x, this thing has to go as 1 over x squared. Now that means we just have to connect these two things together, and that's our plot. Which means then that's what? This is the maximum value at which f is going to be. This is f max, which is then going to correspond to this location here, which is going to be x max. This also tells me that the minimum value in which x is going to be is this value here, because it's 0, and the only other time it's going to go to 0 is way out here at spatial infinity. But since I'm plotting from 0 to 4 times x, or sorry, 4 times d in this case, that means the minimum value is simply equal to 0. That's the smallest this thing is going to be. So for part C, we can then say that x minimum is equal to 0 when the electric field is equal to 0. This is the minimum value it's going to be. The only other place it's going to be 0 is another x minimum, which is all the way out at spatial infinity, or E min is also going to be equal to 0. But again, since we're plotting in the range of 0 to 4d, we're just going to use this one. This is the minimum value which it's going to be. Okay? Now part D then says, what's the maximum value of the electric field? So what is this maximum value? Well, again, we said the maximum value. Sorry, this should have been E, not F. There we go. There we go. So again, the maximum value is going to occur here, which corresponds to this particular x max. So we just need to determine what is x max to then determine what is the maximum value of the electric field. But again, what do we know? We know that here, the value of the electric field, at least its derivative, has to be equal to 0. So we have to extremize our function, which means we're simply going to take a derivative of this guy. So let's take a derivative of him, set him equal to 0. So this is going to be equal to k times q squared times the derivative with respect to x of x divided by x squared plus d squared raised to the 3/2 power. Now, lo and behold, we actually did this derivative before. When we were talking about the force. So if you want, I can do the derivative again. If not, I just let you look back in your notes and go through the derivative. It's up to you. What do you want to do? Want to do the derivative again or just say we've seen this before? Go ahead and do it again. Sounds good, Zach. So let's do it again. So let's do d dx of x divided by x squared plus d squared to the 3/2. And again, that's all equal to 0. Now, as I mentioned when we did this in class, never, never, ever do the quotient rule because it's pointless. Always do a product rule. So the product rule says that d dx of x times x squared plus d squared raised to the minus 3/2 power. So again, all I'm doing here is I'm making this guy multiplied by, which I'm making a negative 3/2 instead. So our product rule says if I have a function which is a product of two functions, I take the derivative of the first times the second plus the first times the derivative of the second. So let's do that. So this is going to be equal to simply derivative of x with respect to x is 1. So this is going to be 1 over x squared plus d squared to the 3/2. That's that one. Plus the function, the first function, which is x, times the derivative of the second. Well, this is x squared plus d squared to the minus 3/2. So if I take 1, I subtract 1 from that, it becomes a minus 5/2. So this becomes minus 3/2 times then x squared plus d squared to the minus 5/2. All times the derivative of the inside, where the derivative of the inside is simply 2x. Okay? That doesn't look like a minus. I mean, make it look like a minus. There we go. So good. What will happen then is that this 2 will cancel this 2. And this will become negative because of this negative. I get an x here with an x here. That becomes an x squared. And finally, this is a 1 over 3/2. This is a 1 over 5/2. So to find a common denominator, that's simply 1 over 5/2. So I'm going to multiply top and bottom of this by x squared plus d squared. So let's do a whole bunch of steps in one. So this becomes x squared plus d squared minus 3 times x squared, all divided by x squared plus d squared, all to the 5/2. Okay? Well, good. Now, this thing is equal to 0 when the denominator goes to infinity or the numerator goes to 0. Which one's going to happen first? The numerator has to go to 0 first before the denominator is going to go to infinity, because the only way this is going to go to infinity is if x goes to infinity. Which means that when we look at this, we only care about the numerator. We can cancel out the denominator. Nobody cares. So this is then equal to 0 is equal to x squared plus d squared minus 3x squared, which is the same thing as d squared minus 2x squared, which means x then is equal to d divided by the square root of 2. That's our value of x, which is going to extremize our electric field. So this is x max. Okay? So now if I want to know what is the maximum electric field, well, x max then is just going to be equal to the electric field that we found, evaluated at x is equal to d divided by the square root of 2. So it's going to be equal to k times q squared times x divided by x squared plus d squared, all raised to the 3/2, evaluated at x is equal to the d divided by the square root of 2. So good. So if I plug this in, this becomes d squared divided by 2 plus d squared, which is the same thing as 3/2 d squared. And this is going to become d divided by square root of 2. let's put all that in. So this becomes E max equal to KQ squared times D divided by square root of 2 times 3/2 D squared to the 3/2. Okay? So this finally becomes KQ squared, let's write it out slowly, D divided by square root of 2 times 3/2 D cubed. Okay? This D cancels out one of those, so this finally becomes KQ squared divided by the square root of 2 times 3/2 D squared. And I'm just going to leave it that way. I could go further, but you know, you guys aren't always as into algebra as I am, so yeah. It's okay? So this is the maximum value of what the electric field is going to be. So any place else is going to go from 0 up to this maximum, and then go all the way back down to 0 as x goes to infinity. Okay? So good, so that's it. So this is electric field from point charges. So again, if I have a point charge, the electric field is simply k times q squared divided by the distance r squared. The direction is either going to be radially outward or radially inward, depending if it's a positive charge or negative charge. Then the total electric field, if I have multiple point charges, is simply the vector sum over all of these guys, the superposition. So the next thing we want to start looking at is, well, what happens if I have an object which is a big fat blob? We call it continuous distributions. So what happens if I have a continuous charge distribution? So for example, there's my continuous charge distribution. So let's say this thing has a total charge of Q, and I want to know what is the value of the electric field at some point P here. So I want to know what is the electric field at point P. This is what we wanted. Well, the way we would do this is, as we talked about with forces, is we would simply start taking this thing and chopping it up into a whole bunch of small delta Qs. Okay? So I'm going to take this thing and I'm going to chop it up into a delta Q. So here's one delta Q. It's called that delta Q1. Another one over here. It's called that delta Q2. Say another one over here. Called that delta Q3. Illustration purposes, I'm just going to do one more. It's called that delta Q4. And then what? So each one of these guys has their own distance away from the point charge, or from the point of interest. So this distance here is going to be the distance R1. This distance is going to be R2. This distance is going to be R3. And this distance is going to be R4. Okay. Now for funsies, let's just say that Q is greater than 0. So this thing is positively charged, which means that since all of these are positive point charges, the electric fields will have to point radially away from it along these lines of connection, which means this one's going to have an electric field pointing this way. So that's E1. E2 is going to be this way. E3 is going to be along this line, so this is E3. Finally, E4 would be something here, so this is then going to be E4. So then the total electric field then will be the vector sum over all of these, which means my total electric field will point something like this. It's going to be E at point P. So this is the vector sum over all these guys. Great, so now what? So this says then, by the superposition principle, that the electric field at point P then, let's say magnitude-wise, is going to be equal to K times delta Q1 over R1 squared, plus K times delta Q2 over R2 squared, plus blah, blah, blah. But this is the same thing then as K times the sum over I of delta Qi over Ri squared. But now, what I want to do is I want to shrink the size of each one of these delta Q's to make this into a sum over an infinite number of delta Q's. Right? So basically what we're going to do now is we're going to take the same thing. We're going to say this is equal to then k times the limit as delta qi goes to 0 of the sum over I of delta qi divided by ri squared. But what's the limit of a sum? So what's the limit of a sum? So I'm making this into an infinite number of summations. An integral. Cool. This is an integral. This is a Riemann integral by definition. So what this says then is that the electric field at point P is then actually equal to K times the integral of dq divided by r squared, all in some direction. I'm going to call that the r hat direction. So we talked about this before, but dq, so what is dq? So dq is the charge of a single element representing the entire charge. What is r? R is the distance from dq to the point capital P. Okay, so r is the distance from that single charge element that we're looking at to the point of interest, point P. Now that brings up further questions as we talked about before. What is dq? Well, dq, we usually turn that into a geometry integral. So typically what we're going to do is we're going to rewrite dq in one of three ways. It's either going to be equal to lambda dl, eta dA, or rho dv, depending on the type of geometry. If my system has line symmetry, then what means we're going to use the first one. So this guy has line symmetry. If my system has an area symmetry, we're going to use the second one. And finally, if this thing has a volume symmetry, we're going to use the last one. So what is lambda, eta, and rho? So lambda, eta, and rho is the charge per something. So here, since this is a line integral, this is the charge per unit length. This is an area integral, so this is the charge per unit area. And since this is a volume integral, this is the charge per unit volume. So lambda then is equal to charge over length, eta is equal to charge over area, and rho is equal to charge over volume. So look, so this says if I have a continuous charge distribution and I want to know the electric field at a specific point in space, I then conceptually wise have to take my object, chop it up into an infinite number of pieces, sum the electric field contributions from each one of those infinite number of pieces together to then create the total electric field at a given point in space. So the thing to pay attention to here is all of this is only true at one given point in space. Which means if I move that point in space, what do I have to do? This all over again. So if I simply move the point from one location to another location, I have to do this all over again. I have to redo this integral. Anytime I move the point, I have to redo the integral. Unless that point is along, say, a particular line where everything works out to be exactly the same. Then I don't have to do it again. But, for example, if I was looking at this pen, and I was looking at the electric field contribution above this center line here, I go through this integral, and then I move that point from this location here to this location over here, I have to do the integral all over again. It will not be the same. But if I was looking above the center line, anywhere I move above the center line, since it's above the center line, the value of the integral will be the same, just the distance will be different. Which means I don't have to redo the integral in that case. Okay with this? Now, one thing to pay attention to with this, though, is that we can't always do every integral. I know your calculus class loves to pretend that we can actually do every integral. The answer to that is actually we can't. Out of the entire space of integrations, we can actually do about this much. That's it. Everything else we have to do numerically. So in this class, everything we do will be in closed form, so you can actually do the integral. But just note in your engineering classes and things when you get in the future, most things you cannot do the integration for. You have to use the computers to numerically solve your integrals. So just be aware of that. So even though calculus likes to pretend we can do everything, we can't. We can only do like this much. So, go. So basically all we're gonna do now is do a whole bunch of examples of this and try to get a better feeling of how to do this. Now, I talked about this before. When it comes to the exams, all I want you to do on the exam is basically set up the integral. That's the hardest part. The rest then is just math. I would love to watch your math skills, because I like math. But we only have 50 minutes to an hour to do an exam. And if it takes you an hour to do a trig substitution, then you're not going to get much done. So again, on the exam, I'm going to simply put the values of all the integrals that you are probably going to have on the first page. So on the first page, there'll be a list of like 4 integrals. One of them will be the correct one. But that'll be, you know which one is the correct one based off of how we set up the integrals. Okay, so we're going to focus a lot on how to actually set up the integrals based off of what the meaning of all this stuff is. So let's do some practice. So the first one is we want to know what is the electric field a distance z above the center of a uniformly charged ring of charge, which has a total charge of Q. So this is the first one we want to look at. So what does this mean? So this means that I have a ring of charge. Here's my ring of charge. This has a total charge of Q. And I want to know some distance z above the center point here. So this is my center point. This is my point P. What is the value of the electric field? So let's say that this thing has a constant radius of capital R, because it's a charged ring. So I want to know at point P here, what is the value of my integral? What's the value of the electric field? So how do we do this? So the first thing we're going to do is draw out a dq. So I'm going to cut this little section here. I'm going to call that guy my dq. Where we choose dq to be is completely arbitrary. Doesn't matter. We just have to have a representation of what dq is. So from this point to the location of the electric, or of the point, so from dq to the point P is the distance r. So this is my distance r. And we know we're looking specifically at point z above here. Now from this guy, this has an electric field contribution, which is going to point radially away. So this is going to be the electric field from that point dq. I'm going to write that as dE. So that is a differential amount of electric field. Now, the next thing we're going to do is, just like we did with point charges, we're going to look for symmetries. We're going to see, does something cancel? And what I mean by that is, what happens if I instead chose my dq to be the symmetric side over here? So if I chose dq to be over here, then this distance here is again the distance r. My dE is going to point in this direction now. So this is going to be the direction of my differential electric field. What do I know is true then about the dE on the right versus the dE on the left? What has to be true about that? What's up there? They're equal. Exactly. They have equal magnitude because dq here is the same as dq here. This r is the same as that r, which means they have equal magnitudes. Since they have equal magnitudes, what then happens to the horizontal portion of the electric field? It's going to cancel, right? Which means that the total electric field, in this case, will only point in the vertical direction. This is going to be the direction of my total electric field, EP. We're going to use that in just a second. Good. So now what we now just learned was that this is equal then to k times the integral of dq divided by r squared. However, we now know that the electric field at point P only points in the vertical direction, which means I have to tack something onto this which says it only points in the vertical direction, which means we need to put a trig term on. So if I define this angle here as theta, meaning I define this angle here also as theta, because those two angles are the same, I need now to say something about this guy. So according to that angle, the one on top, do I want to take the sine portion then or the cosine portion? So I want it to only go in the vertical direction, but where I define that little tiny angle theta up there, the vertical portion corresponds to what? The sine portion or the cosine portion? The cosine portion, good. So what I want is only cosine of theta. So I want to say the electric field only points in the vertical direction. Good. So now what we want to do is, first of all, we have to figure out what is dq. So here we need to know what type of symmetry does my object have. Does my object have line symmetry? Does it have area symmetry? Or does it have a volume symmetry? Now, just to remind you, if I can use this here, this thing is simply a wire bent around in a circle like this, and it has a charge of Q. So if I had a wire simply like this, what type of symmetry does this thing have? Does it have a line symmetry, an area symmetry, or a volume symmetry? I rotated it, I mean. What do you think? So is this a line, simply a bent line? Is it an area, meaning is this portion filled as well? Or is it a volume? Well, we can all safely assume it's not a volume, right? Cool. So that leaves two. Is this thing simply a line, because it's a wire bends in a circle? Is it an area, because there's stuff in here, which there's not? So which one is it? It's a line. Good job. So this thing has line symmetry to it, which means then that's what? Since this thing is simply a ring, this thing has line symmetry to it. It's a one-dimensional ring which goes in a circle, which means then that first of all, dq is going to be equal to lambda dl. The next thing we want to do is rewrite r here in terms of the geometry. Well, here, even though I drew r here, I can also draw r here, which means this thing is simply a right triangle, which means the what? This side is simply equal to r, this side is equal to z, which means that I can rewrite r squared as then being capital R squared plus z squared. What about cosine theta? Cosine theta, we know by definition, is equal to the adjacent side divided by the hypotenuse. But as I said, instead of using that theta up there, let's use this theta here because those two thetas are the same. That way I can rewrite theta in terms of geometry. So according to this angle here, what's the adjacent side? Z, and the hypotenuse is simply r. So this is going to be equal to then z divided by r, which is then equal to z divided by r squared plus z squared square root. Okay? Now, let's put everything together. So this says that my electric field contribution then is going to be equal to k times the integral of dq, which is now lambda dl, times cosine, which is then z divided by r squared plus z squared, square rooted. And then this is divided by r squared, which is then another r squared plus z squared. Or let's rewrite this. This is then equal to k times the integral of lambda times z dl divided by r squared plus z squared, all raised to the 3 halves. Now, in this case, since this is uniformly charged, what that means then is lambda is equal to a constant. Now, when I wrote down those things before about lambda, eta, and rho, those things aren't necessarily always constant. I could, for example, have this ring where half of it is, say, one charge and the other half is another charge. Or it could depend on the angle as well. For example, as it goes around, it could increase charge, decrease charge, increase charge, decrease charge as like a sine, something like that, cosine, etc. But in this case, since the problem said it was uniformly charged, what that means then is this guy is simply equal to a constant. So as far as this is concerned, this guy's equal to a constant. I can pull it outside of the integral. Now, what else? What is DL? Well, DL, so let's draw that on here. DL is simply the length of this little dq here. This is DL. Because dq, remember, is lambda dl, which means that DL is simply the length of this ring here. So let me make a ring on here again. So this is my dq here. DL is simply the length of that dq that I chopped out here. That's DL. Now here, what I'm doing is I'm taking this ring, putting it here, I'm looking at this point here, which means then this distance z, if I chose a different distance z, say here versus here, does that change this dl at all? No, that stays the same. Does that change anything else? No. Z is determined by the fact I'm looking at that point z. R is the radius, that thing is fixed. So as far as this integral is concerned, lambda is a constant, z is a constant, r is a constant, dl is the only thing in which I'm integrating over. Which means that all of this extra stuff is simply a constant. So this is actually the same thing as that's it. This is one of the easiest integrals we're going to do. Because again, here, z, r, and lambda are all independent of dl, which means they're all simply constants, which means I can pull them outside of the integral, which means the only thing I have here is the integral of dl. Well, what's the integral of dl? L. L is simply equal to the length of the ring, but what's the length of the ring? 2 pi times the radius, right? The circumference. So at the end, this thing becomes, vector field at point P is equal to k times lambda times z divided by r squared plus z squared to the 3/2, all times L, but L is simply equal to 2 pi r. Lambda, at the same time, is equal to the total charge q divided by the length, which is the same thing as q divided by 2 pi r. So actually this length cancels this length, which means the length doesn't matter as well. So if I put all that in, this becomes k times q times z divided by r squared plus z squared all to the 3/2. But we said this thing was pointing in, say, the z direction, so this is all pointing in the k-hat direction. This is our electric field. Okay with what I did? So again, all I'm doing here is I'm rewriting lambda as q over L. So that L cancels that L. So all the lengths are actually just going to cancel out. Okay. Let's do a harder one. So the next one says, what is the electric field at a point P, a distance z above the center of a uniformly charged disk? So last time we looked at a ring, this time we're going to look at a total disk. What's the electric field in this case? So let's redraw our picture. So now what we want to know is, here's my disk. Say our disk has a radius of A, just for fun. Actually, it's called R again. Keep it the same. So again, we want to know above the center point here, this is our point P, where this is some distance Z. So this thing, the only difference now is that this thing is a disk instead of a ring. So again, we want to know, again, what is the electric field at point P? So let's talk about this now. Now, here, notice that if I had a disk, which was something which was solid, I can actually create a disk by putting rings on top of each other, right? So if I start off with a ring of 0 radius, and then around that I put another ring, and I put another ring, and another ring, and another ring, and another ring, each one with a slightly bigger radii, I can then create the entire disk by simply stacking rings on top of each other. Okay? So what that means then is we're going to take this disk, and we're going to cut it into a whole bunch of rings. So this is my ring, where this ring here then has a DQ. So this is our DQ. And let's say that this ring has a radius of A, and it then has a thickness to it of dA. So the thickness of this ring is dA, and the radius of that ring is A. So much like last time, R then is going to be the distance from the ring. to the point P. So these are my R's. My electric field contribution then from each one is going to point this direction. So this is my DE. Over here, electric field is going to point DE this way. But again, what happens to the horizontal pieces of the electric field? Again, they're going to cancel, which means that my total electric field, again, is only going to point in the vertical direction, my total electric field. Okay? So, same thing as before, this is then equal to K times the integral of dQ divided by R squared. But again, I need something here that tells me I want only the vertical portion. So I'm going to do the same trick as before. I'm going to call this guy theta here, which means this guy is also theta. And again, we're going to take only the cosine portion. I want only the vertical portion. Is okay? Not too bad. Good. Now, again, first things first is we have to determine what is dq. So a disk has what type of symmetry to it? Is a disk a line symmetry? Is a disk an area symmetry? Or is a disk a volume symmetry? So tilt my water bottle and hope I don't drop water everywhere. Here's my disk. So here, this is again a whole bunch of stacked rings on top of each other. So does this have a line symmetry to it, an area symmetry, or a volume symmetry? Again, ignore this section. Has an area symmetry to it, right? So since this has an area symmetry to it, we're going to rewrite our dq then as eta dA, where dA then is the differential area contained inside of this ring that we drew. So here we're doing is we're rewriting this as eta dA, where dA is the differential amount of area contained inside of this ring. Okay? Good. Now, let's work on dA. What is dA then? dA then is the differential area contained in this loop. Right? Now remember, area is always going to be length times width. Or in this case, this is equal to then length times thickness. So if I have a ring, again, let me make my ring here. So dA again is the thickness of this ring. A is the radius of this ring. So if I want to know the area here contained in this ring, all I have to do then is take the length of this ring times the thickness of this ring. The thickness of this ring is simply dA. What's the length of this ring? If this thing has a radius of A, what's the length of it? So what's the length of a circle? 2 pi times the radius, right? So that means dA then is going to be equal to eta times 2 pi a, since that's the radius of this ring, times the thickness of it, which is simply dA. R squared then is going to be equal to, again by Pythagorean's theorem, it's going to be a squared here plus r squared. So this is then, sorry, plus z squared. There we go. So this is my r. Finally, cosine of theta, as before, is going to be equal to the adjacent side. According to this angle here, the adjacent side is simply z divided by the hypotenuse, which is r. So it's going to be z divided by r, which is then going to be z divided by a squared, thank you, plus z squared squared. Okay? So finally, last thing I have to do is just put all my pieces together into this integral. So let's put everything into that. So what this finally tells me then is that the electric field at point P is going to be equal to K times eta times the integral of dA, we do it in small steps, divided by r squared times cosine of theta. This is then going to be equal to K times eta integral 2 pi a dA times z divided by a squared plus z squared raised to the 3 halves. One more thing. I now need bounds of integration. Because the charge only exists where? The charge only exists on the disk itself. which means I need to integrate this over the geometry of the disk, but our disk only exists between 0 and capital R, which means my bounds of integration on this are from 0 to capital R. So we only integrate over where the geometry tells us the charge exists, which in this case is only from 0 all the way out to the radius of the disk. That's it. Last thing is, what's constant here? 2 pi is constant. Well, what about z? Z is also constant. It's a fixed distance in which I'm choosing the point to be, which means I can finally rewrite this as 2 pi times k times eta times z times the integral then of a dA divided by a squared plus z squared to the 3 halves. And I'm integrating from 0 to capital R. Now, if this was an exam, at this stage, you would now flip to the first page and find this integral. That's what you do on the first page. This is mostly what I want to see you do. This is setting up the integral. At this point, we have exhausted all of the physics. The rest is now just the math. So at this stage, you would flip to the first page, find the integral that looks like this, write down the solution, and go from there. Okay. So this is a little bit different from calculus class, because calculus class, they give you this and they say integrate this. Great. In physics, we want you to set up this. After that, it becomes math. And again, we only got 50 minutes to an hour, so I can't make you do all that in the exam. I would like to. I like that. Everything's okay? So, from here, we simply solve this. We are going to do the math for this, just because it is lecture class, so we can do that. So from here, we're going to do U substitution. Let's use U sub. For U sub, we're going to go ahead and say that U squared then is equal to A squared plus Z squared, which means that du then, so I get 2U du is equal to 2A dA. So the 2's are going to cancel. Oops, 2, not A. So finally, I get U du is equal to A dA, which means this A dA here is going to be simply equal to U du. Down here, this is going to be the same thing as U squared to the 3 halves power, but U squared to the 3 halves power is the same thing as P. So let's plug that in. So this becomes EP is equal to 2 pi K eta Z times then the integral of U du divided by U squared to the 3 halves power, which is the same thing as 2 pi K eta Z integral. So this becomes a U cubed, which cancels out one of those, so it's going to be U over du. So du divided by U squared. What does that mean? Everyone's okay? Last thing is we can change our bounds of integration. So here, since U is equal to this, so that means that when what? A is equal to 0, so let's bring it over here. So when A is equal to 0, that means U is equal to Z. And then when A is equal to R, U is equal to the square root of R squared plus Z squared. So this is going to be integral from Z to the square root of R squared plus Z squared. If you're not very comfortable with changing bounds, don't worry, just bring it back to the original and then plug it in afterward with the original bounds. But so good. So now I have the integral of U du divided by U squared. What's the integral of du divided by U squared? What's the integral of dx over x squared? What's the integral of x to the negative 2 dx? You integrate, you add 1 to the exponent and then divide by that, right? Good. So this is negative 1 over u. So this becomes 2 pi k eta z minus 1 over u, evaluated from z to r squared plus z squared. Finally, we'll plug this in. So this is going to become 1 over z minus 1 over that square root stuff. I can factor out as 1 over z, so that's going to cancel out this z here. So finally what I get is 2 pi k eta times 1 minus z divided by the square root of z squared plus r squared. Finally, we know eta is equal to what? The total charge divided by the total area, but what's the total area of our disk? Just the total area of a circle, which is then just simply pi r squared. So this is equal to then a divided by pi r squared. So plugging this in, we finally get that the electric field then is equal to 2 pi k times eta, which is k divided by pi r squared, times 1 minus z divided by the square root r squared plus z squared. So this pi is going to cancel out this pi, and then finally I get, so this is going to be 2kq divided by r squared times 1 minus z divided by r squared plus z squared, square rooted, all in the k-hat direction. This is our electric field. Okay? So all the U sub stuff, again, I'm not going to make you do it on the exam, but it's mostly just setting up the integrals. Okay. Everyone okay how to set it up? We'll do one more after this one. Or not. Depends on which time we go. So one other thing I want to point out before we move on to the next problem is, it turns out that there's an easy way to check if this electric field makes sense. And the way that this works is we're going to take limits. Now the first thing is, if I have any object and I get very far away from that object, what should that object look like? So meaning if I had even this thing, if I found the, say, electric field from this, but I got very, very far away from this object, what should this object look like? What does the Earth look like very far away from it? What does a chair look like very far away from it? What does a person look like very far away from it? What does any object look like if I get far enough away from it? What's that? Super small, or a point. The smallest anything can be is a single point. Okay? So number one thing is, if I don't trust my electric field, if I don't trust my math, the first thing I can do is I can take the limit that z goes to infinity. In the limit that z goes to infinity, if I get far enough away from it in the z direction, this object better look like a point charge. Which means that if I take the limit of this, as z goes to infinity, this electric field better become kq over r squared, right? Which in this case is z squared. If this does not hold, something is wrong. So if I go far enough away from it in the z direction, this thing better look like a point charge, where we know the electric field is kq over r squared, where r in this case is simply z. What does any object look like if I get close enough to it? So if I get close enough to any object, what must that object look like? For example, we know going far enough away from the Earth looks like a point. We are very close to the Earth right now. What does the Earth look like very close to it? Can we see curvature? No. What do we see? We see flat. If I get close enough to any object, it better look like a sheet of charge. Which means that if I get close enough to any object, in this case, meaning if I take the radius of this object and I blow it out to infinity, so in the limit that r goes to 0, my electric field then better become a sheet of charge, which we now know is simply eta over 2 epsilon naught. If these two limits do not hold, you're doggone messed up somewhere. Okay. This electric field is not correct. So if you ever write down an electric field and you do not trust it, you should not trust it ever. Might have made a mistake. That's somewhere. These are the two limits you have to check. You want to go infinitely far away from the object, meaning that you're going to let the z in this case go to infinity. Or sorry, that should be infinity, not 0. There we go. If we let z go to infinity, this thing better look like a point charge. If I go close enough to the object, which is the same thing as z goes to 0, or in this case, the radius goes to infinity, so 0 on both of them, it better look like a sheet of charge. Right? Now, we don't have time to check these limits. We'll do that Wednesday, just to verify, to show you how all this works. Typically, that means you have to take a Taylor series expansion at some point. I know y'all love Taylor series expansions. So we'll do that on Wednesday first thing, and then we'll do one more example of a continuous charge distribution just to get a little more practice on this. And then we'll talk about more things. Everyone's okay? Well, super excited to do math at 9 o'clock in the morning.